We learn static electricity. Today we're going to learn electric current. But first, we're going to make a connection between static electricity and electric current. And then we'll try to understand three types of circuit: series circuit, parallel circuit. Put them together, we're going to call it complex circuit. We're going to start our conversation with static electricity. So now, last time, static electricity, and then today we're going to learn electric current. There are 4, 5, 6, however many we can think of. First thing we can think of definition. What would be the definition of static electricity? Let's say the definition of static electricity: building up of charges on a surface. What would be the electric current? Electric current would be the flows of charges from location A to location B in a given amount of time. Okay, so that's pretty simple, pretty obvious. Now, next thing we can think of duration. All right, so this doesn't last long. Static electricity doesn't last long. How long it does last? Oh, well, it's very temporary. It lasts as long as you discharge them. How can you discharge them? Okay, we saw that. You take a copper and, well, let's not take copper. You take a PVC pipe and you take PVC pipe. You rub them against each other. There would be no transfer of electron because both have the same electron affinity. However, if you take the PVC pipe and animal far and rub them against each other, there would be a transfer of electron from PVC pipe to PVC pipe from animal far, because PVC pipe has greater affinity for electrons. So PVC pipe will end up gaining electrons from animal far, making animal far positively charged and PVC pipe negatively charged. And how you can discharge them? By grounding them. If you touch the PVC pipe with, I don't know, with electroscope, then all the extra electron can move to electroscope. You can say that that's conduction. So you can discharge them. So what happened? Those building charges, they only until you discharge them. All right. Okay. So electric current, they flows as long as you have the power. So flows as long as you have power connected. To the circuit. All right, what else we can think of? Well, I can think of cause. What causes the static electricity? Okay, causes, as I said, that rubbing, right? Rubbing causes the static electricity, right? But rubbing between two different objects causes the electricity. Rubbing between, I don't know, PVC pipe and PVC pipe will not cause static electricity. So rubbing between two objects with different electron affinity. What causes the electric current? What causes electric current is the voltage. Voltage causes the electric current. And what is voltage? We're going to try to understand that in a few seconds. Right. Okay. So let's continue with this. We have few more. Maybe example. What would be the example? What would be the example of? What would be the example? What would be the example? The example would be static electricity. Example would be lightning, right? Why lightning? You have a cloud, right? You have a cloud, right? So cloud are negatively charged. Okay. If negatively charged, if it is negatively charged and it accumulate lots of negative charge in the cloud, then it always grounded with with the ground, with the earth. So with the earth, okay, and then uh, what happened? The earth takes all the extra electron, and the process, in this process, you see, we human perceive that as lightning, or maybe you can experience every day, and that is shock, electric shock. Okay, so if you touch a doorknob, what happens? Sometimes you experience that you uh, it's like you experience electric shock. Why is that? Because, for example, you walk on the carpet, right? All the electron transfer to your body through shoe. Okay, uh, why is that? Because you have a different affinity, electron affinity. Okay, so loss of electrons, enter into your body, you are now negatively charged, including your hand. Now if your hand touches the doorknob, which is metal, then all the electron transfer, making you what? Neutral. And this process, which you experience as shock. The example of this one would be light. Okay. All right. So now 1, 2, 1, 2, 3, 4. Let's think about path. This no closed path required. Closed path needed. But this one, yeah, you need a closed path. And what do you call it? Circuit. One more, movement. All right, I cannot think of anything else, but one thing, movement. This is charge at rest, and this is charge in motion. Now, okay, so we make a connection between the static electricity and electric current. So now is the best time, is the time to start with circuit, a closed path. Okay, so it's a polygon. Let's start our conversation with polygon. It's a closed path. Now we're going to turn it to a circuit. Before we do that, I'm going to introduce 3 persons involved with this discovery. Number 1 is Alessandro Volta. He discovered voltage. He discovered battery, actually, and battery is the source of voltage in year 1800. This is physical quantity, and this is the SI unit. This is volt. The year of the discovery and physical quantity. Okay, so Alessandro Volta invented battery in 1800. Okay, that's good. And the second person we're going to be talking about, Henry Marie Ampere. Around 1820, he invented current. The symbol for voltage is V, symbol for current is I, and the SI unit for current is amps, after his last name, of course. The third person we're going to be talking about, Greg Ohms. And what did he discover? Resistance. Okay, so what year? 1820, 1827. Of course, we call, what is the SI unit? Omega. Okay. All right, so these 3 persons we're going to be Their ideas gonna be we're gonna be talking about their ideas. Okay, so let's go back to our circuit. uh, this is not a circuit, this is a rectangle made of a conductor. Let's say it's made of aluminum. But before that, let's talk about an analogy. All right, so let's talk about a road. Okay, from, I don't know, home to school, right? From home to school. So let's say you take a car to come from, let's say, not home to school, home to work. So from location A to B, there are other car, of course, but you are here in this car in right here. You are here. You don't care about this guy, or you don't care about this guy. You only care about yourself, right? Your main goal is to get to the work as soon as possible. So what would be then flow of traffic? Flow of traffic from your perspective. From your perspective, the flow of traffic is, all right, yourself over time. How can you write that? How fast you can move from, or I can move from location A to location B in a given time. All right, so that's can convert to this. However, there is a problem. This is a very selfish definition of flow of traffic. This is your point of view, but this is not a universal definition of a flow of traffic, because there is a cop, of course, traffic police. If you ask traffic police, is this the definition of flow of traffic? He or she will say, no, of course not. This is a very selfish definition of traffic, of flow of traffic. So what would be the universal definition, or the definition with respect to the traffic police? It would be what? Number of cars, or maximum number of cars can move to. So number of cars move to a given amount of time. If there is no traffic police, and if you try to execute, if you want to put your interest in action disregarding other people's interest, then there will be lots of accident. Then the flow of traffic would be zero. Why is that? Because everybody would try to get to the work as fast as possible, causing lots of accident, making in the long run the flow of traffic zero. So the universal definition of flow of traffic would be number of cars can over given amount of time, and the traffic police is there to enforce the traffic rules. Good. Now this definition we're going to turn it to the electric circuit definition. All right, so how fast okay, instead of this we're going to say that number of flow of charges, or number of my car, how fast my car. Instead of how fast my car, you're going to say number flows of charges from positive terminal to negative terminal in a given amount of time. And you see these and these are almost the same. So you can, if you can write the definition, you should be able to translate it to an equation, and that would be the current is charges over time and number of charges. Okay, not only one charge but number of charges. Good. So now that we have the definition and we have some idea, we should be able to see the diagram. And this rectangle is made of what? Aluminum. Okay. All right. So first we're going to put the battery, which was invented by Alessandro Volta. So positive terminal, we're going to call it positive terminal anode, and we're going to call it cathode, negative terminal. So the charges moves from positive terminal to the negative terminal. These are what? These are atoms, right? Why there are atoms? Because aluminum is made of atoms. How many atoms? Billion, billion, trillion. We're not going to count them, but a finite number of atoms. So this aluminum wire, you can take this aluminum wire, and then you can cut it with scissor, and you can make a straight line from this aluminum wire, and you can say that the length of the aluminum wire is 10 meters. And this aluminum wire, the geometric properties of this aluminum wire, it has the cross section. If you take a very sharp knife, you can cut those cross section. If you take one of the cross section, it's gonna look like a circle. And this one has properties. Circle has a property: circumference, area, and so many things. So let's say area, and then it has a diameter. So let's say 3 millimeters, right? And since it is made of aluminum, the resistivity it has. And the resistivity is rho. Rho is a Greek letter. And the resistivity for aluminum is 2.8 times 10 raised to negative 8 ohms times meters. Okay, now we want to find the resistance in this wire, which is 10 meter long, which you use to create this circuit look like a rectangle. So then you have rho L over A. So what is your rho? Isaac, you done? How much longer? Okay. Are you getting distracted? Okay. R is rho, which is of course 2.8 times 10 raised to negative 8 omega meter, and we never found the area. Area is pi r squared. If the diameter is 3 meter, then radius is 1.5 millimeter, and which is as a unit is, which is equivalent to 0.0015 meter. So you're gonna write 10 meter, and you're gonna write area, which is 0.0015 meter. Okay, PL over A. Oh, there is a mistake. Pi is 3.14, and this R is 0.0015 square. So 3 times 15 is 7 times 10 raised to negative 6. I believe it's 7.2, but 7 times 10 raised to negative 6 is good enough. So you're not going to put radius over here. You're not going to put radius 0.0015. Why would you put radius? You're going to put the area, 7 times 10 raised to negative 6 meter square. One thing you notice is meter square, they cancel. All right. So without using calculator, you can say instead of 22.8, you can write 28. You can do whatever you want. 7. But you always going to keep in mind you did not write 2.8, you wrote 28. So this has to be 10 raised to negative 8, negative 9. Negative 9, positive 1, positive 6. So what do you get? Positive 7, negative 2, 4. So R is equal to 4 times 10 raised to 7. So R is equal to 0.04 ohms. What does that mean? The resistance is now 0. There is a resistance. Good. Because the temperature is now 0. So what we learn, the resistance depend on material, the wire made up. So resistance depend on a material, wire made of. In this case, aluminum. It also depends on radius. It also depends on, okay, so it depends on rho, it depends on radius or area, radius. It depends on length, and it also depends on temperature. What does that mean? If you have a 0 Kelvin, which is negative 273 Celsius, if you increase the temperature, let's say 20 degrees Celsius, which is the room temperature right now, at room temperature it is, I don't know, 0.04 ohms. If you decrease the temperature, this one gonna be 0 ohms. If you increase the temperature, I don't know, then it would be, if you increase the temperature 100 degree Celsius, this is gonna be 0.04 plus 0.04 ohms plus R, and this is, you will never be able to get there. Why is that? Because this is called Bose-Einstein condensate. Bose when we are talking about state, you know, there are 3 states of matter. What are the 3 states of matter? You have solid. If you heat them up, what do you get? Liquid. If you heat them up, what do you get? Gas. If you heat them up, what do you get? Plasma. If you take plasma, cool it down, you get gas. If you take gas, cool it down, you get liquid. If you take liquid, cool it down, you get solid. If you take solid, you cool it down, you get Bose-Einstein condensate. What happened at Bose-Einstein condensate? Bose-Einstein condensate, you see the atoms, right? They vibrate. Why do they vibrate? There is a friction in the classical mechanics. Classical mechanics. In a classical mechanics, the wire, this wire made of aluminum, it doesn't matter, copper, zinc, iron, wire can be made of anything you like. Aluminum is a conductor. It made of atoms. Even the insulator also made of atom. I also made of atom. You also made of atom. This chalk is made of atom. But the chalk is in that sense, there is no differences between chalk and me. But that's topic for another time. These atoms is vibrating. Why? Because there are frictions. So the loss of energy lost, okay, the loss of noise, loss of energy lost, and inside the atoms there are electrons. Of course there are nucleuses inside the atoms, but we don't talk about nucleuses because number 1, neutron doesn't have charge, number 2, proton don't move. So we are only left with the electrons. Electrons only move. And when we talk about the quantum mechanics, this is classical mechanics, this is the quantum mechanics. In classical mechanics, we call them ball, small ball. In quantum mechanics, we call them waves. We no longer call them balls, we call them waves. Why do we call them waves? Because they show the wave-like behavior, like the water in the ocean. Why we call them ball? Because they show like the small spear type of behavior, like a marble. When you roll marble, it doesn't show the water-like behavior, and when you see the water in the ocean, they do not show like a marble-like behavior. So there are differences between the balls and the waves. But when you in the domain of quantum mechanics, you call these balls the waves. Now here, why do you need voltage to move the electrons? You need voltage to move the electrons is because there is a friction. If you do not, if this chalk will stay here forever unless you move them. So how can you move them? Well, you have to have acceleration. Acceleration will give rise to velocity. Velocity would give rise to what? Displacement. See? And this acceleration came from where? Acceleration due to gravity. And that velocity that give rise to velocity, and that velocity give rise to what? A displacement. It fell. Good. So you need voltage. Here you don't need voltage. Why you don't need voltage? Because there is no friction. Why there is no friction? Because with very small temperature, like when the temperature is 0 or very close to 0, there is no vibration between who? Between atoms. We no longer call them atoms, we call them waves. There are no vibration between waves. So what happens if there are no vibration to the waves? There is no energy needed, energy required. Why? Energy required because there is no vibration. So they are like sitting, those atoms, we call them waves, are like sitting on the couch and relaxing, watching TV. And how that help us? That help us because the waves do have the wavelength. The wavelength grow bigger. So the wavelength of one wave go bigger. The wavelength of other wave also go bigger. The wavelength of other wave also go bigger. So they are now overlapping each other. And if you zoom in, you're going to see as if you don't see any balls. You're going to see probably one thing. That's how it's going to seem like. That's how it's going to look like. That's why you call it condensate. Condensate means that it's very packed. Atoms are very packed. There is no gap between them, and there are gaps. Today we're going to talk about classical mechanics, not the quantum mechanics. That's the topic for next time. Okay, so let's continue with the classical mechanics. What did we learn so far? We learned that the temperature increases, the resistance increases, temperature decreases, the resistance decreases, temperature 0 degree Kelvin, then what happened? The resistance is 0. You call it superconductor. And now let's come back to classical mechanics. So you're going to have the battery. We're going to call cathode. We're going to call anode. We're going to call cathode, and the electrons. These are charges. The charges carries the electrons, and electrons move fast like the crazy car driver on the road, but due to the traffic police, there is a check and balance. The driver don't drive as fast because the speed limit sign. And if they don't have the cops on the road, there would be more accident, there would be less flow of traffic. If there is no police officer over here, then there would be, what are we going to call it? Resistor. Then the electron going to move fast. Since there are resistor, electron will not move as fast. Good. Even if electron move very fast, they will slow down over here because this is like a police officer. If you don't have resistor, there would be like loss of accident. We call them short circuit, fire in the circuit. Good. So now you have a voltage, you have a resistance, and there is a product. As charges move from positive terminal to negative terminal, then what happened to the and what do you get? You get current. Okay, so there is a Ohm's law. We talked about Ohm's earlier, and Ohm's law, 1827. We got the Ohm's law is a triangular relationship between voltage, current, and resistance, VIR. That tells you that voltage is current times resistance. Current is voltage over resistance, and resistance is, of course, voltage over current. Good. Now, we're going to divide our idea into two circuits. This is you're going to call simple circuit with only one resistor. We're going to call one bulb. One bulb. Now we're going to divide this to two system. We're going to call one going to be look like this. This is positive. This is negative. This is bulb number one. We're going to call resistor one, which is 3 ohms. We're going to call resistor 2 or bulb number 2, which is 6 ohms. And we have the same idea over here, a little bit different, probably plus minus. We have, okay, so we're gonna call this one 3, R1 3, and R2 6. We're gonna give some rules. First, what do we observe? We observe what is the similarity. The similarity is both has voltage. What does that mean? Voltage is equal to voltage 2. That means they both have the same voltage, same magnitude of voltage. Okay, if one is 24, other is also 24. They both have the same number of bulbs, same number of bulbs, and they both have the same magnitude of bulb. Bulb 1 is 3 ohms, bulb 1 is 3 ohms, bulb 2 is 6 ohms, bulb 2 is 6 ohms. Okay, what are the differences? Now discover the differences. This one electron has only one path. If you are electron, you are in a bad shape. Why? Because if there is an accident, then you cannot move, then the whole house is going to be dark. You are in a good situation over here. If you are an electron, if you are taking this path, if this one is broken, you always can go back, use this path. It's like a driver who takes a path and there is an accident and multiple roads lead to your work. You always can take the other road, end up at your work. And this, if you take this type of path, you will never end up at your work if there is an accident, because there is only one road. Good. All right. We're going to discover more differences. Let's write them down. Number one, we're going to say the current is same across the circuit. How can we write that? We can write that is like current is equal to current 1 plus current 2 is equal to current 2 is equal to plus n is equal to n. Okay. It's like there are 10 students in the class and all got 100 in the test. So Joe is equal to Jack is equal to Julie is equal to Molly is equal to Kelly is equal to Noli. Okay. Number 2, voltage drops. Voltage drops. What does that mean? V is equal to V1 plus V2 plus Vn. How I can show voltage drops over here? So voltage 1 is equal to 8 ohms and voltage 2 is equal to 16 ohms. What does that mean? If the voltage at location A is 24, let's say this is 24. Okay, at location A is 24. So this one get 24. This one consume 8. 24 minus 8 is 16, and this one release 16 for this one. This one consume 16. Get 16, consume 16, it release 0. All right, there is a voltage difference. We call it potential difference. So by the time you get here, right here is 0. So this 24 and 0, this potential difference, what we call as pattern. Okay, good. So you see the voltage drops. Okay, this voltage drop, you're going to learn it in a few seconds. Okay. Number 3, resistance. Resistance increases as you add more bulb. How can you write that? R is equal to R1 plus R2 dot 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 Rn. On the other hand, if you come over here, Isaac, you done? You done? Oh, then can you go to your fluid? Can you make your fluid lecture? Okay, make your fluid lecture. All right, so number one, you're gonna do what? Current is shared by who? Bulbs, different bulbs. How can you write it? Current is shared by different bulbs. Number two, voltage same across the circuit. How can you write it? You wrote it before, so you kind of know how to write it. V1 is equal to V2 is equal to so on, Vn. Number three, what are you going to do? Number three is resistance is reciprocal. How do you want to do that? Resistance is which is 1 over R is equal to 1 over R1 plus 1 over R2 plus dot dot 1 over Rn. What does that mean? Resistance is reciprocal. What is the reciprocal of 2? 1 over 2. Reciprocal of x, 1 over x. Good. Now, if you add more bulbs right here, what happened? Right here. All right, they go dimmer. If you add more bulb over here, they go brighter. Good. Now is the best time to write more rules. And how can we write more rules? Let's write it over here. Hopefully you can see all those board at the same time. Okay. So we have few rules for series, for parallel. Okay. For series, we have current is equal to current 1 is equal to current 2. Voltage is equal to V1 plus V2. For resistance, you have R1 plus R2. For the Ohm's law also give us power is equal to VI. So power is equal to V. Well, we're gonna give you the power in a second. So the current is equal to current 1 plus current 2. Voltage is equal to V1 is equal to V2 and so on. The resistance is reciprocal. Don't forget that R1 plus R2. Now let's do the power. So we're gonna write. We're gonna solve the power equation. So power, we're gonna start with VI. Power is equal to VI, and power is equal to VI. Right? What is the true? Many things is the true, but one thing is more true over here is that the current is same. Okay, so we're gonna keep the current, we're gonna replace the voltage. Okay, what can we replace the voltage with? We're gonna replace the voltage with IR. So power is equal to IRI. So the power is equal to I square R. Okay, this is the equation for series. Many things is true, but what is the most important true over here is that the voltage is the same in a parallel circuit. So we're going to keep the voltage, we're going to replace current by V over R. So we're going to replace the current by V over R. So voltage and V over voltage and current is V over R. So the power is V square over R. Good. Now we're gonna now ask ourselves few questions. Number one is, which one gonna be brighter? If you look at the series circuit. Series circuit, you see two bulbs. Which one would be brighter? Okay. So now our hypothesis is, in the series circuit, this one would be twice as bright. In this one would be twice as bright. This one would be twice as bright. Okay, now good. You hypothesize that this one is twice as bright, but how do you know? Okay, series. Use the series equation. P is equal to I square R. How many bulbs? 1, 2. So Yeah, it's very simple. You're going to say P1 over P2 is equal to I square R1 is equal to I square R2. Current is same, so you can cancel current, but this is not 1. This is 6. This is not 2. This is 3. So this is 6. This is 3. I square cancel. 3 goes to 6 twice. So P over 6 over P over 3 is equal to 2 over 1. This is twice as big. In a few seconds, we're going to mathematically prove that this is actually true. And when we said that twice, we exactly tell you the amount. How are we going to do that? By, of course, using the power equation for parallel. Power equation for parallel is P is equal to V square over R. How many bulb in bulb? 2. So you're going to say P1 over P2 is equal to V square R1 over V square R2 is actually not 1, is 6, and it's 3. This is then 6. This is then 3. So you have P6 over P3 is equal to V square R6 divided by V square R3. V square cancel. 3 goes to 6 twice. So what are you left with? P6 over P3 is equal to 1 over 2. So this one is twice as big, and that's exactly what we said. Now we're going to mathematically prove that this one is actually twice, and we know the value. Okay, so to do that is very simple. All right, so it's very simple. How can you do that? All right, so let's do VIR. All right, so we have a VIRP. We have bulb 1, we have bulb 2, we have total. Okay, we have VIRP. We have bulb 1, bulb 2, bulb total. Okay, what is true? This is series. Current is same, but the resistance is very easy to calculate. Why is that? Because you're just going to add them up. So R1 is 3, R2 is 6, so this must be 9. Okay, Ohm's law tells us finding the current is easy. Voltage, let's make voltage 24 volt. 24 volt, as we said that V1 is equal to V2. Current is 24 over 9. Where does 9 come from? Total voltage. So this is the current is same across the circuit. So this is 24 over 9. This is 24 over 9. 24 over 9 plus 24 over 9, 24 over 9. Why? The current is same across the circuit. We said that 10 students in the classroom all get the same score, 100. Voltage drops. So how can we find the voltage? To find the voltage is you're going to use the Ohm's law, current times resistance. So we have voltage is equal to current times resistance. So what is current? Current is 29 over 24 over 9. 24 over 9. Resistance is, of course, 3. 3 goes to 9, 3 times. 3 goes to 24, 8 times. So this is 8. That's why earlier when I said what is the voltage over here, voltage is 8. This one received 24, this one consume 8, this one releases 24 minus 8. Okay, now let's find the voltage over here at bulb number 2. Current is same, 24 over 9. Voltage is resistor is 6. Okay, so now you have 3 goes to 3 3 goes to 9 3 times, and 3 goes to 6 twice. 3 goes to 24 8 times. 8 times 2, 16. That's why earlier I said this one gonna get 16, this one gonna consume 16, and this one gonna release 0. So 18 8 plus 16, which is of course 24. Okay, now power you can do VI is also power. You can do this one, I square R. So they're all going to give you the same thing. I square R is equal to VI, which is equal to VI. V is 8 times VI, 8 times 24 over 9. 8 times 24 over 9. Okay, I will just write 8 times 24 over 9. Okay, I'll write 8 times 24 over 9. 8 times 24 over 9. Okay, that's all I'm going to write. B is 16, 16I. So 16 times 24 over 9. Okay, we already proved that. Wow. 8 times 24 over 9 and 16 times 24 over 9. So as you see that this is twice as bright than this one, and that's exactly what we said. This is twice. If this is 16 times x, so we can say 8x, and this is 16x. So this is twice as bright. There you go. Okay, and then we're gonna add them up, 8x, 16x, and then we're gonna say the power is 24x. And x is of course x is of course 24 over 9. 24 over 9. Yeah. Okay. There you go. So now let's go over here. What is the easiest things to find? 24, because voltage is same across the circuit. Now we're going to do the resistance. Resistance is 3 plus 6 is 2. How 3 plus 6 is 2? Let's see. 1 over R is equal to 1 over R1 plus 1 over R2. Okay, so 1 over R is equal to 1 over 3 plus 1 over, of course, 6. So 3 and 6 LCD is 6, 2 plus 1. So 1 over R is 3 over 6. So R is 2. Okay, so there you go. That's why we said that as you increase the bulbs, the brightness increases. Of course, for this reason, current will not be same. Currents would be shared across the circuit. The bulb will share the current. So the current is, we know that the current equation V over R. So you're going to write it down. Current is V over R. So the current is, V is of course 24 and R is 3. So 8. The current is V over R, 24, and this is what? 6. So 4. So 4. So total current would be 4. Okay. So now we're going to find the power. Power is voltage times current, 24 times 8. Okay. So you're going to call 8x. 24 is, let's say 24 is, x is 24. Okay. I don't have calculator. I'm not going to be able to do that. So we're going to call 8x. 8 times 24. And this is 4 times 24. Okay. And then we're going to say just 24 is x, 8x. X is 24, 4x. Okay. So 8 plus 4, which is 12, 12x. Now, what do you observe? You observe that this one twice as great as this one. Who is twice as great? Bulb with resistance 3. Bulb with resistance 3 is twice as bright. And bulb with resistance 6 is twice as bright. We're going to end over here.